right, what we're talking about today is a new unit. This will be a lot of review today. We're going to focus on phase changes and the energy changes that are involved in phase changes. So a lot of what we're talking about today is review stuff, but it's been a while. We talked about phase changes at the very beginning of the year, so way back in August and September. So we're going over some of that information again. We'll go over some of our gas laws information again, and then starting kind of on Wednesday, we'll be doing more new stuff. Do you remember what the phase changes are? Condensation is one. Evaporation. Sublimation.
Sublimation.
Freezing.
Freezing.
No.
There is something with a D. Deposition. I think melting is the only one we missed. So looking at phase changes and the energy changes that are involved with them. To talk about energy changes, we need to talk about the difference between potential energy and kinetic energy. Most different kinds of energy that you deal with can be categorized as either potential or kinetic. Potential energy is usually described as energy that is stored. If you go on to take physics next year, we'll talk about energy that is stored when an object is above the ground, like at a height. It has a certain potential energy. When we're talking about chemistry, potential energy is the energy that's stored in a chemical bond. Atoms bond to decrease their overall energy. There's some amount of energy that's stored within that bond. So potential energy is energy that is stored. When we talk about breaking bonds, we talk about energy having to be absorbed. When you're breaking bonds, it's kind of like pulling two magnets apart. You have to put energy in to do that. They don't just fall apart on their own. And when we talk about energy being absorbed, we're saying potential energy, because that's energy that's involved in that chemical bond or being stored in that bond. When we talk about forming bonds, then we're talking about potential energy being released. All atoms bond to decrease their overall energy. So when they form bonds, potential energy is then released. Kinetic energy is the other big kind of energy. Hopefully we remember that kinetic energy is energy of motion. When you're talking about physics, that could be a car or a person in motion running or driving down the road. When we talk about molecules, molecules can have three different kinds of motion. They can vibrate. Molecules, for example, in a solid will vibrate. They shake back and forth in place just a little bit. Rotating would be just turning in a circle. And translating means moving from one spot to another. So when we talked about the motion of gas molecules with the gases unit, we focused most on molecules that were translating or moving from one spot to another. From the beginning of the year, we talked about how different phases of matter have different amounts of energy. Gases have the most kinetic energy because they have the most freedom to move. Then liquids, then solids have the least. Also at the beginning of the year, we talked about two vocabulary words, exothermic and endothermic. What do those mean?
Going in, heat going out.
Enter heat.
Heat or energy going in or going out. Exothermic is which one?
Exit.
Exit, so energy or heat leaving. Exothermic processes give off energy. Energy is released to the surroundings. Exothermic processes, or one example of an exothermic process, is bond formation, because we just pointed out that when bonds are formed, energy is released. You can also describe some of the phase changes as exothermic. When you change from a gas to a liquid, or a liquid to a solid, or even a gas to a solid, we used to say that there were bonds forming. When we first learned about this way back at the beginning of the year, we described this as bonds forming between the molecules. We're going to change that wording a little bit now because now we know better. We know that bonds are the things that are inside the molecules. The forces that hold molecules next to each other are intermolecular forces. So instead of saying bond formation now, we can say intermolecular force formation. The other side of that would be endothermic. Endothermic means? Entering, energy in. So these are the processes that absorb energy. Energy is taken from the surroundings. This would describe processes where bonds are breaking, because you have to put energy in to pull bonds apart. It also describes some of the phase changes. If you're going from a solid to a liquid, or a liquid to a gas, or a solid to a gas. Again, when we first learned this back at the beginning of the year, we described these processes as breaking bonds because the molecules were getting further apart. But now we know better. We know that bonds are the things that are inside a molecule. The things that hold molecules side by side are intermolecular forces. So when you change phases, we're not really breaking bonds, we're breaking intermolecular forces. Do you remember BARF?
Yeah.
What's it stand for?
Bonds absorb energy and bonds release energy.
Right, breaking bonds means energy is absorbed. Forming bonds means energy is released. You could swap out the word bonds for the words intermolecular forces and it would still work the same. When you break intermolecular forces, energy has to go in or be absorbed. When you form intermolecular forces, energy is released or given off. So the breaking side is endothermic, and the forming side is exothermic. Let's review our 6 phase changes. We've seen this picture before. What do you think goes in the boxes? Gas, liquid, and solid. With a picture for each one. Remember, solid atoms or solid molecules are going to be close together. They're touching. They're in an organized pattern. Solids will hold their own shape and have a definite volume. All of those are properties we learned about solids. The atoms or molecules in a liquid have a little bit more freedom to move. They can slide past each other. They are a little bit more randomly arranged. They still have a definite volume, but they take the shape of their container. So liquids have to be in something. Gas molecules or atoms have the most freedom to move. They will expand to fill their container, so they have a variable volume and a variable shape. And they are the most randomly arranged. If you go from a solid to a liquid, what's that called?
Melting.
Melting. Liquid to solid? Freezing. Gas to liquid? Condensation. Liquid to gas? Evaporation. These are the harder ones to remember. Solid to gas? Sublimation. And gas to solid? Deposition. This diagram is organized so that all of the inside arrows are things that are exothermic. You have to take energy out or remove energy to get that process to occur. For example, if you're going to freeze a liquid, generally, what do you have to do to it? Remove heat or make it colder. So you're taking energy out when you do that. When energy is released, that means there's an overall decrease in the potential energy. That energy is leaving. All of those processes on the inside arrows involve forming intermolecular forces. IM forces, intermolecular forces. When you bring molecules closer together, think about going from a solid to a liquid to a solid. You're locking them in place, you're forming those forces, which results in things that have more order. They are less randomly arranged. The particles are closer together. They have less freedom to move. Everything on the outside arrows would be just the opposite. The outside arrows are the things that are endothermic, where you have to put energy in to get that process to occur. We think about something like evaporation. Evaporation is going to happen a lot faster on a sunny day when it's warm outside, because there's energy going in, maybe to a rain puddle, and it would make it evaporate faster. Energy going in means you have an overall increase in potential energy. That energy can be used to break intermolecular forces, to pull molecules apart from each other, which results in things that are less ordered. That means the molecules are more randomly arranged and they have more freedom to move. And that's because the particles would spread out. They'd be getting more space in between. Here's where we're bringing in a couple of the things that we talked about during gas laws. There is a difference between the word heat and the word temperature. When you talk about raising the temperature, usually we kind of think about that as being synonymous with putting in heat. Heat and temperature. We usually, in casual speech, will interchange those words. But when we're talking about it in science class, there's a small difference between those two things. Heat is the actual form of energy that would be going in or coming out. Energy is measured in different units than temperature is. Energy can be measured in a lot of different units. The science ones are called joules, named after a scientist. He was French. Symbol for that is a capital J. It can also be changed into kilojoules, which would be 1,000 joules, just like a kilometer is 1,000 meters. Other units for energy that you might be a little bit more familiar with here include things like calories. Calories measure energy in the food that you eat. If you deal with, or if you know anything about furnaces or air conditioners, sometimes they measure energy in like BTUs, British thermal units. There are a lot of different units that you can use to measure energy. Joules is the one that we use most in science. But that's different still than what you measure temperature with. What do you measure temperature with?
Degrees.
Degrees, usually Celsius or Fahrenheit or Kelvin. So the units are different. Heat refers to the actual energy that is moving or being transferred from object to object. Heat always flows in this direction. It always flows from the warmer object to the colder object. What's that?
Because the colder objects are absorbing it, right?
The colder object is absorbing the heat. So when you hear somebody say in the middle of the winter, shut the door, you're letting the cold in. No, you're letting the heat out. Heat always flows from a warmer object to a colder object. If you pick up an object, or you pick up maybe an ice cube and you feel like it's cold, it's because that object is sucking the heat out of your hand. That's why you feel like it's cold. Temperature is a little bit different. Temperature is not the energy itself. Temperature is how we measure that energy, and specifically, temperature is a measure of the average kinetic energy of the particles. So what does that tell you about the particles?
Are you moving fast or slow?
Yeah, how much they're moving. Are they moving fast or are they moving slow? How much particles are moving? Temperature and heat are related. If you increase the heat, if you give particles more energy, they're going to move faster, and you will see the temperature rise. But they are slightly different. Heat is the energy itself. Temperature measures that energy. So the relationship between heat and temperature is if you give energy to the particles, they will increase the amount that they move, and you will see an increase in temperature. Heat is the energy, temperature measures the energy. There's a small difference there. Just a little bit more. This one goes back to gas laws. What are the main scales that we use to measure temperature? Celsius and Kelvin. We don't really use Fahrenheit so much in here because it's science class. We use mostly Celsius or Kelvin. What's the difference? Why do we need two scales? We have two different temperature scales because of the way those two different temperature scales can reflect what's actually happening to those molecules. Kelvin, the Kelvin scale, is a more direct reflection of kinetic energy. 0 on the Kelvin scale means 0 motion of the molecules. 0 on the Celsius scale just means what? Yeah, you're about to go negative, water's freezing. It's a pretty common temperature. 0 on the Kelvin scale is actually 0 motion. It's a more direct reflection of what the molecules are doing. One comparison that I use with these two scales is the difference between looking in a regular mirror, maybe at home in your bathroom, and going to a fun house and looking in one of those regular, or not the regular ones, but the wavy ones. When you go and look in a fun house mirror, can you recognize yourself? Yeah, but what's changed? It looks distorted, right? Some of them make you look short and skinny, some of them make you look tall. It just depends on the curve in the mirror. You're still recognizable, but you're distorted, you look funny. If you look in a regular mirror at home, in the bathroom mirror, it's a pretty good reflection. It's pretty much what you look like. That's Kelvin. Kelvin is a good direct reflection. Celsius is the funhouse mirror. It works, it's still recognizable, but it doesn't give you as clear of a picture of what those molecules are actually doing. A little bit more review. Some temperatures we should know. 0 on the Kelvin scale is called absolute 0. That's the lowest temperature that we know of. All molecular motion stops. A couple other temperatures we should know: the freezing point for water and the boiling point for water. And how do we get between those two scales? K equals C plus 273. Okay, that is it for our review. Starting on Wednesday, we'll be doing a little bit more new stuff.